We're going to debate about spectral methods now. We're going to shift gears. So the idea is, behind this course in general, is the following. I want to teach you, or convey to you, sort of the major computational methods available to you. One of them is finite difference. It's what we've been looking at for a while now, right? Sort of these, we've been looking about stability schemes and so forth, discretize in space, discretize in time, finite difference. Anytime you discretize in space, you have your scheme with some prescribed accuracy, and it works. You construct matrices to carry all the information about how the stencil works. Now we're going to shift gears to spectral methods. And spectral methods aren't confined necessarily just to Fourier transforms. A lot of times you think about spectral methods, and to a lot of people, like even me, typically my first thought is Fourier. Okay? But that's not always the case. But we are going to talk mostly about Fourier in this class, and for very specific reasons that hopefully will be just so crystal clear today, you'll be yelling at the end of class. I can totally tell it's going to happen. All right, so ready? Spectral methods. So let's talk about Fourier methods for a moment. So the idea behind Fourier was the following. If you remember, we wrote down, we already talked about a Fourier transform before. Here it is. Here is a Fourier transform pair. But what today we're going to learn is why does it work and why do we care about Fourier in particular. So the Fourier transform pair takes a function, let's say a spatial function, and it integrates against this kernel. And this kernel is e to negative ikx. It's cosines and sines. That's all that is. So what you're saying is, let's take this thing, integrate against a bunch of sines and cosines. That's where Fourier comes in. And I get out a function of k. Now k itself, what is k? What does k represent? K represents wave numbers, right? So when I think about this function here, this is things like cosine kx minus I sine kx. Frequency content. So what you've done is you've taken a signal or a function or anything you want to, whatever this represents, and you've decided to say, I will take this thing and rewrite it as a bunch, I'll transform it to frequency content. And I'm going to say that's how I'm going to capture all my information. I'm going to rewrite everything as frequency content. Okay? So by the way, this is very natural. So for instance, when you think about a bird chirping, which I'm sure you do all the time, right? When you take a measurement of that bird chirp, right, and you want to plot it, you don't plot the pressure waves and how they're changing in time. You plot the spectral content, the frequency content of what that bird is saying, right? So it's natural to think about having stuff represented in frequency space versus time domain or spatial domain. So this is a Fourier transform pair, and this tells you how to get out of the frequency space, which is to say, take your collection of frequencies, integrate now against this kernel again, but now with a plus sign, and now you get back out the original function. Okay? In and out of frequency space. And that's what you need to know how to do. Now, one very major relationship that came out and that we've been using is the following. That the Fourier transform of the nth derivative is ik to the nth power times the Fourier transform of the function itself. And this is gold. You may not recognize it as gold, but this is gold right here. Okay? This is an amazing result. This is why we use, there's two reasons we're going to use the FFT. One is this result. Two is going to be the speed. It's going to be very fast to do this. But first we're going to set it up and talk about why is it fast. But here's gold result number one. Okay? And if I had a gold pen and if I thought it'd show up on this whiteboard, I would have a gold pen and write it just to, hammer that home in your head. Okay. Now, a couple things we got to talk about now if we're going to go to do computing on this thing. So first of all, infinity doesn't exist in your computer. Negative infinity, infinity, that's fine and all good on paper. And you're doing calculations on paper. But when you tell the computer to say, hey, I'm going to compute on, no, you're not. Okay? One integral would take you infinity amount of time because it would, your computer is dumb enough to keep going out to infinity. Right? So this is not what you're going to do. You're always going to truncate to a finite domain. 1. 2. Frequencies. Notice that you're integrating here over all possible wave numbers. Like for instance here, I'm going to integrate when I go back all possible frequencies. No, you're not. You are going to pick a finite number of frequencies on a finite domain. Period. So once you have that in your head, that this is a theoretical conception, but when you work at it in practice, you have to also work on a finite domain, X, with a finite number of points, with a finite number of frequencies on a finite domain. That's how you do computation. Okay, so what we're really talking about then is, what did those theoretical formulations really mean to you in terms of MATLAB? Because all you care about is, what does MATLAB think a Fourier transform is? Okay, right now, that's our business. We're going to apply this routine here, which you've already done. And the question is, what does that do? What does this do? Okay, so we need Fourier transform pairs that account for the fact that we have a finite number of points, finite number of frequencies, finite size domain. And here it is. You can do a help, FFT, okay, on your MATLAB computer, and stuff like this will pop out. In particular, the formulas will pop out, which is, here is the Fourier transform from the point of view of MATLAB, a computational point of view. So here, let me write it down, and then we'll talk about them. Here's the Fourier transform pairs. Does that silence make you a little uncomfortable? No? You guys are perfectly fine with just sitting there in silence. Because it makes me a little uncomfortable. All right, I'm just being honest. Here we go. Fourier transform pair. Now let's talk about what it does. So first of all, we think about this function as being a function defined on a grid of points, n points. Okay? N goes from 1 to n. So this is like when we chop up our domain. Here's your x, and you chop it up into n points. Okay? So what I do is I take my function at each one of those points, and I'm basically, here's my integral, right? The integral is just a sum. But now it's, instead of an integral, remember, we're undoing all of calculus. Differentiation and integration can't be done on a computer in some sense, right? Because they involve taking things going to 0 or infinity. We don't do that. What we do is say, let's go back to first day of calculus, and this is how we did an integral. We just said an integral was a sum of stuff. Here's the sum of stuff. And if you took this to be n goes to infinity on a finite domain with small dx's, you'd say it's an integral, which is right on the other board over here. But here, we're not doing that. We're saying here's the function, multiplied by the kernel. And what it does essentially is, here's your kernel, e to the I, and these are your frequency content pieces. What it assumes is that what you have are Fourier modes that live on a 2 pi periodic domain. Your FFT believes you are on a 2 pi periodic domain. Okay? So you have to set up, generally you're not going to be on a 2 pi periodic domain, so you better fix it so that you are. Okay? So if you remember in our notes, we did a 2 pi over L, right? Rescaling. That's so we can work with the FFT. The FFT assumes that you are 2 pi periodic. So this is how you basically take a function and you write it in frequency space. And there are how many modes of this? There's a total of n of them. So you pick 64, 128, 256, whatever you try to pick. You pick it. There's all your frequency content. And if you want to go from your frequency content back out, here it is. Fourier transform pairs, the computational way of thinking about Fourier transforms. Finite number of points, finite number of frequencies, finite size domain. And then you get to pick how big your domain is. You get to pick how many points it is, but they have to be finite. Okay? So, that is your Fourier transform pair from the point of view MATLAB. Okay? So just that you know that.